Everyone, so today we're going to be talking about the dot product and just kind of getting the equation, linking it to an angle. So we know this formula here, but we're going to try and come up with an approach, a sort of an explanation to this equation, because it's a weird thing we do here. I mean, you just take these two and times them together, then take these two and times them together, and then add them up. Okay, and you can do this with, three-dimensional vectors, four-dimensional vectors, and so on. So let's try come up with a little explanation for this. So the first thing, just going to consider two vectors in this little xy kind of space. Okay, again, two-dimensional vectors, but we can extend this to more dimensions. Let's just do 2 dimensions. So we have this part here. I'm going to call A, vector A. I'm going to call this A1, A2. And the vector B is just going to be B1 and B2. So let's go here, find this vector and this vector. So we have a horizontal vector and upwards vector. So the upwards vector here is going to be, it's just going to be A2, isn't it, right? And then this vector going horizontally is just going to be A1. Okay, it should technically be 0, A1 and 0, sorry, A1, 0. So yeah, I guess I'll write that. And then here as well, got the same thing going on. This has got to be B1, 0, and then this is going to be 0, B2. Okay, so we've got our vectors here. Let's just consider more angles. So we're looking at this angle alpha, this angle beta. And we realize we've got, a few 90-degree angles. We've got these 90-degree angles here, 90-degree angles are lovely, right? Because there's a lot of things we can do. And the first thing we can do is we can get an equation that links all the angles together. Alpha plus beta plus theta equals 90 degrees. And we already kind of got an equation for theta. All right, there we go. That's our equation for theta. The thing you have to understand is because we want to try and link the dot product to an angle. Okay, so the best thing we should do is try get an angle and see where we go. Okay, see where we go. All right, let's go ahead and let's keep moving. Let's just take the cosine of both sides. And a really useful identity to know is that when you have sine, or it could be sine or it can be cosine. I will go cosine because that's what we're doing here. That is identical to, actually, yeah, we'll go sine. So sine of x is identical to cosine of 90 degrees minus x. Very useful to know. And yes, you can say the same thing with cosine, like so. Do know this identity, very useful, and we're going to be using it here because we got that form. We've got 90 minus some angle, and we know because of this identity, therefore cosine of theta is just going to be equal to sine of alpha plus beta. And when we're adding two angles together, that should become pretty obvious that we should be using the double angle formula. So we're going to be using sine of alpha times cosine of beta plus sine of beta cosine of alpha. Okay, there we are. Okay, now we need to get an expression for sine of alpha, cosine of beta, sine of beta, cosine of alpha, but that's actually pretty easy because we've got everything here we need. Okay, we've got a bunch of right angle triangles, so we can just do a lot of trigonometry. So let's just do it to the side here. Got sine of alpha. That's just going to be equal to opposite over hypotenuse, which is going to be equal to A1 over, and this has a length, right? So we need to take the modulus, all right? So modulus of A dash. Now, really what we're doing here, the modulus, is we're just doing Pythagoras, doing A1 squared plus B1 squared, square rooted. Okay, that's what we're doing here. But we just like to write it like this because it's neater. Okay, that just means a distance. This distance here. Okay, let's carry on. Cosine of alpha well, that's just going to be instead A2 over the modulus. Okay, that's exactly what we're doing here. Great. Next one. Sine of alpha, yeah, cosine alpha, let's go to sine of beta. Okay, we're going to do that here. Sine of beta is opposite over a hypotenuse, but opposite is going to be B2. So we have B2 divided by mod B. Okay, mod B. And then same here, our sine of alpha, our cosine of beta is going to be equal to B1 over the modulus of B. Great, so we got everything done. Now we literally just plug it into the equation. Cosine of theta is just going to be equal to sine alpha times cosine of beta. So we can sort of do this cross multiplication here. So we get A1 B1 over this, okay, timesing the two modulus together, and then we're adding the other multiplication, so we can do another little cross multiplication here, plus A2 B2 over these two moduli, I think is the plural, and then we get cosine of theta is equal to A1 B1 plus A2 B2 divided by the two moduli times together. Okay, so that's a nice little equation, but we can do even better than that. What we could do is we can use our little definition of the cross product here, or sorry, the dot product, where we just times these two vectors together. And you can notice that that's literally what it is. I mean, you're doing A1 times B1 plus A2 B2. That is what we've defined over here to be the dot product. Okay, and what that is that's A dot B. So let's just rewrite that. Therefore, cosine of theta is equal to A dot B over this. And there we go. That's our little sort of proof for that. I think that's really nice. And it can be any dimension. You can do this in 3 dimensions, and it'll just tell you the angle. Now, just a quick side note with the angle. If you have two vectors like so, and you find angle theta, you could also alternatively find that angle as well, okay, which is 180 minus theta. Okay, so you have, this will give you theta, will give you an acute theta, and it will also give you an obtuse theta, depending on what value of cosine you want to choose. And I guess that's kind of like, if you look at the graph, you can sort of see that. Okay, if you choose for some theta, for example, there are going to be 2 solutions. But yeah. Alright, so yeah, thank you for watching, guys, and I'll see you in the next one.